Welcome Calculus AB. We're continuing from the last section. So I want to do an example here, and using rectangles, I want to find the upper and lower sums of a region bounded by the graph of f of x equals x squared, the x-axis, and 0 to 2 on x. So I'm going to draw a graph. I'm going to draw a rough sketch of this. So the curve of x squared is about like that. We're going from 0 to 2. We'll call 2's out here. And it's going to be the area under this curve. And if we, using the rectangle approximation, the inscribed rectangles are going to be like this, and then the next one's going to go like that. And we're going to have shapes like this. Oops, but it shouldn't have gone. And these would be even rectangles. Mine might not quite be even, but you should have shapes that generally look like this. So that would be, so the area of all those rectangles. And the upper limit would be the circumscribed rectangles, which were the right endpoints going to hit the graph. So the rectangles would look like this, maybe going down. And again, this is just a really bad drawing. Yeah, just like that. So let's do one at a time. First thing I got to figure out is what's the width of each rectangle going to be? Because it doesn't say I have to have 5 rectangles like the last example. It's unknown. Since we have unknown, we just make that a variable, where n equals the number of rectangles. And since the length of this, or the total width of the whole thing is going to be 2, it's our width of a rectangle. We're going to call this change of x is going to be 2 divided by the number of rectangles n. Cool. So that means let's do the upper limits first. It's the uppers, which is going to be the right endpoints. So we're going to call this right, which in this case is going to be upper. Doesn't matter if you know if it's upper or lower. Just let's pick right endpoints first. So the formula for the right endpoints, and we're going to call this uppercase M. It's going to be, well, basically you're starting from 1 off and 1 off and 1 off. So this is going to be 2 over n times I. Sweet. So now let's use the summation notation. It's going to be the sum from I equals, starting at 1 to n, because we don't know, of the function f of 2i over n times the width right here. This is the height. The width is going to be 2 over n. Cool. So let's figure this out. F of 2i over n, well, f is x squared, so that's going to equal the sum of x squared, so that's going to be 2i over n squared times 2 over n. And clean that up a little bit, I'm going to get the sum of 4, and 4 times 2 will be 8i squared over n squared. And I can rewrite that and just take the constants out, 8n squared times the sum of I squared. Cool. Now I have to go back to those formulas in that one page. So you wrote down your notes. The sum of I squared from I equals 1 to n is going to be, this will be 8 over n squared, and times n plus 1 times 2n plus 1 over 6. This looks fun. So if you're going to do this, and I want to expand this top part, it's going to be 8 over n squared times 2n cubed plus 3n squared plus n all over 6. Okay, so maybe just write what that expands to save work in the future. Okay, let's simplify this a little bit, and if you take an n out of each of those terms, and the 8 divided by 6, you will get 4 over 3n cubed times 2n cubed plus 3n squared plus n. Oh, this was 8n cubed. My bad. I messed that up. Oh yeah, because I forgot the n's up here. And so another way to rewrite that, if I want to distribute all those, is going to be 8/3 plus 4 over n plus 4 over 3, n squared. Cool. That is the sum where n is however many triangles. All right, I am going to do the left-hand side endpoints. So the left-hand side endpoints are going to be the lower bound right here. I'm going to do that work and try to do it right over here. We're going to go left, which is going to be the lower, and where your basically the divisions between each of those, your m is going to be, instead of this case, it's going to be I minus 1 times 2 over n. Because you're not starting at 1, 2, 3, like you're starting at the endpoint over here. So you got to subtract 1 from it. We're starting at 0. So in this case, if that's my m, I'm going to use my summation notation from I equals 1 to n. And it's going to be f of, one way to write this is 2 times I minus 1 over n times 2 over n again. Stop doing that. Okay, and another way to break this up, going back to our notation here. So the f of that, since it's going to be squared, it's going to be the sum of 4 over n squared times I minus 1 squared times 2n. Okay, and let's break this up a little bit more. I am going to write this as 8 over n cubed times the sum, since those are constants, I'll take them outside. And I'm going to expand this. It's going to be I squared minus 2i plus 1. That's when I equals 1 to n. And that does not mean like imaginary I. Alright, and we go back and use our formulas here. And you can go back and reference those. And I want to kind of skip ahead a little bit here. But if you work this out at home, kids, you will get 8/3 plus 4 over, or minus 4 over n plus 4 over 3n squared. Cool. So it's almost the same formulas here, right? They're kind of similar, but one is plus and one is minus. Now I'm going to ask you a question on this. So you had plus or minus right here. What if you had an infinite number of rectangles? So n is infinity, and if it was plus or minus, this wouldn't matter, right? Because this term goes to 0, and this term goes to 0, and it's going to equal 8 over 3. Well, guess what? If I just integrate this function, x squared from 0 to 2, you get x cubed over 3 from 2 to 0. So you'd get 8 over 3 minus 0, so you get 8/3. Whoa, that's the same exact number. So this kind of proves our integration a little bit in a way, where if you want to find that region under a curve or the area under a curve, if we're doing the summation notation but we have an infinite number of rectangles, we're going to get closer. We're going to actually get the answer if we just integrated using analytically like we did before in section 4.4. So the formula for the area of a curve, or the area of a region under a curve, is basically that.